Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrenner, and in this video, I'm going to discuss using an operational amplifier to implement an instrumentation amp.
This is a very useful amplifier. It's often called an instrumentation amplifier. And you can see this one has three operational amplifiers in it, so it's a little bit more complicated circuit. I'll tell you the end result before we start is that we have a gain is equal to V out over V1 minus V2. That's why it's called an instrumentation amplifier, is it allows us to very precisely amplify a value V1 minus V2. Okay, so let's look at how we would solve a circuit like this. Like many kinds of analysis, one of the things we can do is break it down into smaller parts. So I'll go ahead and draw some circles around this. We're going to have this part on the back side be analyzed separately. Okay, and then if we look at the front side, the input side, we can see that this is actually very similar. Okay, look closely. We label the input minus. They don't have to be in the same position on the triangle. So when we look at this, we see that these are actually the same circuits, right? With a resistor in between. So we can model that by splitting that resistor in half and looking at one of them, and you'll have the same result for the other. So how we can draw this is something like this. This is the input side. Okay, we're going to use symmetry, so that allows us to break that middle resistor in half for the analysis part. And then we have it for both of those op amps. Okay, and then this is just the circuit I designed on, I circled on the previous slide. Okay, we will call the output of each side, we'll just call it something like AV1 of T, where A is the gain of this circuit. Okay, so then for the back half of the amplifier, we can just plug in the two values with the gain shown. They will have the same gain if we choose the resistors to be the same, which is what we've shown. Okay, so let's just look at the input side first. Okay, we're just going to look at this right here, and I've redrawn it or copied it over, and I'm going to call this, for the time being, we're going to call it V of T. Okay, remember the things that we know about analyzing amplifier circuits. The current going in here is 0. The current going in here is 0. This V minus is equal to V plus because we have negative feedback, as I've told you, and I'll just make a little note here that IN is equal to 0. So these are the things you always want to remember. The next thing we're going to do is nodal analysis, and we're going to do nodal analysis at this point right here, and I'm going to call that point, I'm not going to give it a name for now, okay? We'll call it something in a minute. Just a reminder, this voltage here is V of T, this voltage here is V1. So you'll see right away why I chose not to name that dot, the node that I colored blue. So the voltage at V plus is V1 of T, so the voltage at V minus must be V1 of T, based on our assumption that we have negative feedback, and then this is the model for an op amp. So that voltage, V1 of T, is actually the voltage at that node that I colored blue. Okay, oops. So I'll just rewrite it here, V1 of T. So I've got a lot of V1 of T's all over the place, but that's okay. Now we're just going to write a nodal equation here. Okay. We just write V1 minus V over R2 plus V1 minus 0 over R1 over half, V1 minus 0 over R1 over 2. And of course, this current here is equal to 0. So we don't need to add that in. Okay, so we have a very, very simple equation right here. So that's the only nodal equation we really need for this analysis. Now the next is just algebra. So what we need to do now is multiply this equation through by a half to clear that denominator, and we get V1 over 2R2 plus V1 over R1, and then we take the V to the right-hand side is equal to V over 2R2. Combine our fractions, and we end up with this. Okay, and we will just define that to be A. So we're going to define our gain A to be the gain V of t over V1 of t. And then when we solve this, we can write it as in a different form as 1 plus 2 times R2 over R1. Okay, so there is our equation for the input side. And of course, remember, we have two of these. Now let's look at the output side. Okay. Now, for this analysis, I'm naming this V1 and V2 because that's how you would typically see it. It is a differential amplifier. Sometimes you just want a differential amplifier. So we'll substitute in the actual names of those related to the other when we put it all together. So let's analyze our circuit. Now, things to remember, of course, V minus is equal to V plus. Input current into both the terminals is 0. Okay, so let's just start with what we have and write some nodal equations. Let's start by writing an equation here at V plus. Okay, that's called V plus. And we'll get V plus minus V1 over R2 plus V plus minus 0 over R3 plus 0 equals 0. Okay, so we have this voltage, V plus minus V1 over R2, V plus minus 0 over R3, and the current going out here is 0. So we can take that and massage it a bit, and we will end up with this equation right here. Okay, you could have also used voltage division and just write the equation, but if you don't remember how, just do it using nodal analysis. I went ahead and rewrote this by dividing through by R2 because that's often the form you will see the gain of a differential amplifier written as. Okay, so that's something to keep in mind. But it doesn't matter in terms of your analysis. You could, if you didn't know what you were doing, you could always just leave it in this form. It just changes the algebra a bit. Okay, the next thing we want to do is write the equation at this node. Okay, so we will get V minus V2 over R1 plus V minus V out over RF plus 0 equals 0. Now, you can manipulate this with the algebra and you will end up with, you can choose to end up with that equation. Okay, and that's just by collecting like terms and relating them. But you could also get this equation directly. Let me explain how to do that. We would have a current here of 0, of course, and that means that the current from here to here is equal to the current from here to here. So V2 minus V out over those two resistors in series is going to be equal to V minus V out over RF. Again, if you don't want to do it that way, that's okay. You could just take this equation and rewrite it. Again, it changes the algebra, and I probably wouldn't actually try to get that point, but just so you can follow along with me. Okay, so we take this value, we'll take this equation, rewrite it, and we can end up with V minus in terms of V2 and V1. So we rewrite this equation and we get this expression. Okay. Then again, just like often is the case, dividing 3 by R1 is a little bit more how you would see it if you were looking up documentation. Okay. So now all we need to do is take this value and this value, okay, and set them equal, because we know that V plus is equal to V minus. Since V plus equal to V minus, we set them equal, and then you can solve for V out. Again, this is a lot of algebra, and it looks worse than it is because I've divided 3 by the R2 up here and the R1 down here. But again, that puts it in a more standard form. So there's our expression V out in terms of V1 and V2. So this, again, when we're looking at gains, we want to look at the output in terms of the input. In this case, we had 2 inputs, but I told you before we started it was a differential amplifier. Okay, but you would see that here, that you're looking at a difference between values. So here's our expression for V out. Now, if we make a few assumptions, it makes the circuit look a lot simpler, okay? We'll just say R3 will be equal to RF, R2 will be equal to R1, and that gives us a ratio of R3 to R2 is the same as RF to R1, and we end up with a very, very simple expression, okay? So all we do is in this expression here, substitute R3 for RF, and R2 and R1, and then you end up with a very convenient expression. This is why we call it a differential amplifier. It looks at the difference of the inputs, and then it amplifies it by the ratio of RF to R1. Now, if you wanted to, you certainly could leave it more complicated. There might be applications where that's needed, but a plain old differential amplifier is often all you need. So let's get back to our instrumentation amplifier. This has got all the different components. Here's our differential amplifier that we just wrote the equation for. Here's our input side amplifier that we broke into halves, okay, and analyzed separately. So when we did that, we ended up with this gain here, or this output value of this first stage, A V1 of t, and this voltage here would be A times V2 of t. A is the same if R1 and R2 are the same. And so then what we need to do is take these values and use them as the inputs to our differential amplifier. So when we analyzed the differential amplifier, I think we called it V1 and V2. Of course, it was a different V1 and V2. So now we're going to say this is the input and this is the other input. And when we do that and make the assumptions about the values, remember that the gain was RF over R times V1 minus V2 for that particular, the inputs to the differential amplifier. So we have RF over R times the difference between the inputs to the differential amplifier, which in this case are AV1 minus AV2. Take the A out, of course, and then rewrite A. We had a gain expression for A. Just plug it in, and this is what we end up with. And then we can write V out. This was V out, right? So we could write V out over V1 minus V2, and that'll just be this part right here. So there's our gain expression for the entire instrumentation amplifier. So that was a long example, but it did a couple of different things. First of all, or second of all, we derived the gain equation for a differential amplifier. That is a useful design by itself. Then we also added the inputs to it so that we have what we call an instrumentation amplifier. So hopefully after this example, you know that you can solve complex op-amp circuits and these are DC, right? And they only have resistors. And we will use KCL to do that, okay, and Ohm's law, and that's all you need.